Let's do a Bitcoin transaction. I'm on Coinbase and I'm sending $10 worth of Bitcoin from my wallet to my father's wallet. This won't make him rich, but it'll help us explain how the blockchain works. So I'm paying with Bitcoin. The amount is $10. And here I am pasting his wallet address. So you can see that $10 worth of Bitcoin was sent to his wallet address, and it says this transaction usually takes about 30 minutes. So let me pause the recording here, and we'll come back when the transaction is confirmed. So here we're on blockchain.com, which is a blockchain explorer for a lot of different cryptocurrencies. Specifically, we're using Bitcoin Explorer, where we can explore different blocks, transactions, and addresses. So I'll paste my father's wallet address here, and we can see that this is the address. The Bitcoin received was this much, and we can see that in the transaction so far there is one confirmation. Coinbase requires 3 confirmations for it to be officially mined. So here we have our wallet address and the transaction that this address was a part of. So I can click on the hash of the transaction, and it takes us to this page here. Scrolling down, we see that this transaction's hash was included in block 710207. Take a close look at this long string. This is what is called the hash of the block. Notice how many leading zeros are here? 20 to be exact. This block has been recently mined. At a high level, mining is when a miner has successfully computed a hash that has a specific number of leading zeros. The amount of leading zeros is referred to as the difficulty level. We will cover what is a hash and how it relates to mining in a later part of this video in more detail. So we built this tool to play with various components and technologies used in blockchain. This tool is based on an open source library from Anders Brownsworth. The link is in the description, so please feel free to get your hands dirty by going through these simple tools like linked list, encryption, message signing, blocks, and blockchain. For the purpose of this video, let's head straight to the hash demo. In order to grasp what blockchain technology and cryptocurrencies are, we have to start with an understanding of what a hash is. Hashing is when a given input gets converted into a different value. A hash is a digital signature of some input, which means that the data that is hashed will continue to have the same hash value unless something is added or removed. Hashes are also used for safely sending and storing data, and it's very computationally difficult to compute the original text from the hash. If we take a look at the screen here, we see that there is a word, hello, in this data box. This word is being hashed using an algorithm that develops that hash. The algorithm that is in use here is called SHA-256 hash. This algorithm is one of the most popular hashing algorithms and is also used in Bitcoin and many other blockchains. SHA-256 takes the input and it converts it into a hash that has 256 bits, which is 64 characters. If we remove this here, if we look at the hash of hello, we see that it is 2CF24 and a lot of other characters. If I remove this, it results in a different hash. And if I type hello again, we see that it is 2CF24DBA. And it's the same exact hash that we saw earlier. And that's why it's often referred to as a digital fingerprint or signature of data. If we decide to remove everything and we type a few characters at a time, so A has a hash of CA978, I can add B to it, FB8E2, C results in a completely different hash, and so this is meant to show you that adding a single character or removing that character results in a completely different hash. Now, what if I even want to add the entire English dictionary or every page on Wikipedia? It will still generate a hash of the same size. So let me delete this and let's copy some random very large text and paste it here. So pasting it here, that resulted in a hash which is 256 bits or 64 characters. Let's use the concept of hashes and apply it to blocks. So here we have a block, and you can see that it's very similar to the hashing example we just looked at. This is the block number to represent which block it is. Next we have the nonce. Nonce stands for number once. We'll cover nonce in a bit. Next we have the data box, which can be anything, but for this example we have two transactions, transaction 1 and transaction 2. This hash is the hash of these three things combined: block number, nonce, and the data box. So what is this mine button? Let's try it out. Notice the changes? We've got a new nonce value, and the hash now has 4 leading zeros. Behind the scenes, the mining algorithm went through and tried different values of the nonce until it got a hash that had 4 leading zeros. We set this difficulty level of 4 to make it easier and faster. In real life situations, it can be 20 zeros and can take a lot of computing power and time. Let's try to mimic this behavior by hand. So I'll try out different nonce values. So we'll try 1, no 4 leading zeros. 2, we still don't get 4 leading zeros in the hash. 3, no. 4. 4 is an interesting number for the nonce as it resulted in 2 leading zeros. And so earlier we discovered some nonce values which have varying numbers of leading zeros. So we saw 4 has 2 leading zeros, 15 has 1. We can try 880. Oh, not 1. 880. That results in 3 leading zeros. And we'll try one more. 1, 5, 0, 3, 4, 1. And that resulted in the correctly 4 leading zeros nonce value. Now obviously manually guessing takes a lot of time, so that's why the automatic mining step is very useful. This is just a demo, but in real blockchains like Bitcoin, the number of leading zeros can be a lot more than 4. If we take a look at the first block ever mined, referred to as the Genesis block, we see that there are 10 zeros, leading zeros. Meanwhile, we can see the most recent block mined has 20 zeros. The blockchain system enforces the number of leading zeros pattern to control the mining speed. So that covers what one block is. Now let's try to understand how this block is used in a blockchain. Here is a blockchain or chain of blocks. We have our first block here, block number 1, and it has this value as a nonce. There's a data rectangle, but the new aspect of the blockchain is right here, previous, right above the hash value. I'll explain what this is shortly. So we can take a look and we see that there are other blocks as well. Block 2, block 3, and block 4 are here for the example. If you notice something, you see that all blocks have different hash values as well as different previous values. And if we take a closer look, we see that the value for the previous label is the same hash value that the previous block has. So for block number 4, if we ignore the 4 zeros, we see that the previous hash value is listed as EAC36. The previous block has a hash of EAC36. We can look at the previous value for this block as 9382. The previous block has a hash 9382, and so on and so forth until we reach block number 1. And if you see, this is actually how they are chained together, and it's how the term blockchain came into play. The first block actually has no previous block, so the value for previous is actually all zeros. Notice how the first 3 blocks are mined due to the 4 leading zeros in their hashes. In this demo, we showed a mined block with a green background. However, the last block is not mined, which means it is still accepting new transactions. We are showing unmined blocks with a red background. So let's add a new transaction. So I'll go in here and I'll add transaction 3. One of the most, and now I'll actually mine it, so I'll mine it. One of the most powerful aspects of blockchain technology is the chain of blocks is immutable or tamper-free. Let's try something. Let's try to change the data for block 2. So I'll go in and I'll remove transaction 2. And notice how this block and the subsequent blocks are in invalid states or are considered broken, as seen by the red color. No problem, I can remine all of the broken blocks again. It'll take some time, but so what? So now I'm remining those blocks. So now they're all in a valid state. Does that mean that anyone can change the transactions in a blockchain, mine them again, and remain unnoticed? The answer is no. Why is that? Because in a real blockchain system, there are thousands of copies of each chain distributed all over. All copies are identical at all times. This is something called distributed blockchains. Here is the demo for distributed blockchain. We are showing here 3 copies of the blockchain. These copies are seen as peer A, peer B, and peer C. In reality, there are hundreds or thousands of copies, but for simplicity, we're only showing 3. All copies of the blockchain are identical. How can we confirm that they're identical? Well, if the hash value of the last block is the same across all copies or peers, that means that the chain is valid or unchanged. So this one is C719, if we ignore the zeros, C719, and C719. Let's try something. Let's try changing one of the blocks in peer A. So I'll go to block 3 and I'll remove transaction 2. Notice how this copy of the blockchain became invalid because the hash of these blocks isn't satisfying the leading 0 condition? The hash of the last block in peer A is different from the last hash of the other peers. 0CCD is different than C719, which is found in peers B and C. So these two are the same. Let's correct peer A's chain by remining the impacted blocks. So I'll remine this. And I'll remine this. Even after remining, this hash is different from the corresponding hash of the other peers. See how these two are the same? C719, C719, and these two are different from the first one, which is FF59. By the majority rule, the blockchain copy of peer A will be outvoted and rejected and probably kicked out. So far, we have been showing fictitious examples as transaction 1 and transaction 2 for data. Let's take a look at how these transactions look in a relatively real blockchain. Here is the distributed blockchain with transactions in real currency. These transactions can be in any currency or even commodities. For simplicity, we're only showing 2 peers or 2 copies of the blockchain as peer A and peer B. So if we take a look at how these transactions look like in the blockchain, in block 1, in the first transaction, we see that $10.50 are sent from James to Bob, $6.45 are sent from Sophia to Jane, and $12.25 are sent from Paul to Emma. Just to recap, this hash is the SHA-256 value of this block number, this nonce, these transactions, and the previous hash value. If we take a look at the transactions for block 2, $8.25 were sent from Emily to David, $7.50 were sent from Julia to David, and an example of a transaction for block 3 is $12.75 were sent from Rose to Chris. So let's say that one of the transactions in block 2 is tampered with. So instead of saying that Tom sent $15 to Grace, we now tamper with it and change it to 10. Once again, we see that this copy of the chain becomes invalid because the hash values do not meet the leading 0 criteria. So let's fix the chain and remine the affected blocks. Remine that, remine this one. Again, based on the consensus, peer A's copy of the chain will be marked as invalid because its hash value of the last block will be different from the corresponding hash in the other peers. So this demonstration shows how the blockchain demonstrates immutability. Before we wrap up this demo, I want to compare the simple blockchain model with a real blockchain. Number one, in a real blockchain will also validate and make sure that everyone started with the correct initial balance. Number two, there will be thousands of blocks in one chain. Number three, there will be hundreds or thousands of peers having identical copies of the blockchain. Hopefully with this demonstration, you now understand how a blockchain works. I highly encourage you to play with the various tools provided in the description.